gentlemen, welcome to our show and tell. We've had, well, maybe 5 and something weeks of the workshop, and today you'll hear what the results are going to be, what the results are. You see the super something. The workshop, as you perhaps know, is structured in such a way that there are teams that solve particular problems. The problems themselves have been selected at a meeting in November, where we invited various experts and government sponsors and other powerful people to kind of debate and decide what's worth working on. The workshop itself has both professional people in the field and graduate students and even undergraduate students. The undergraduate students are selected in a international search. The graduate students are usually students of some people who are on the team themselves. We then have 2 weeks of pre-workshop to set up our software facilities and to introduce the students to the problems, and then the real workshop starts. I can't tell you now what the dates were, but anyway, it started 5 weeks ago on Monday. So today we have the problems that we worked on are speaker identification or recognition, speech recognition of Arabic, parsing with live supervision, and I don't know, summarization for the purpose of machine translation. And today is a day for speech recognition. The first team, as you see, is international, and the team leader is Doug Reynolds, and he's going to talk to you about speaker identification and recognition.
Let me lead into the final report for the SuperSID team. First, I just want to overview the people who are on the team. They're easily identifiable by their dashing attire. We had a great group of people here. We had our senior members. I'm not going to go through these again. You can see them sitting in the middle here. 3 grad students coming in, working with our team. 2 very good excellent undergraduates. And of course some remote affiliates that are working here. So let me say a little bit about the talk today. I'm going to be the main MC for going through this. As a team, we chose to have one person more or less present all the work because we all worked on various different components of it, and we decided that to have an integrated presentation, we would have me up here getting all the chance to show all this great work that we've done. But everybody's contributed on this. We will have the undergraduates present some of their work and what they did this summer when it's appropriate inside the talk here. And then after the coffee break, we're going to have the graduate proposals where they'll both summarize what they did this summer and give a proposal for future work. So this is an outline of the talk that I want to go through this morning. In the introduction, I just want to resync everybody to what the problem is that we're addressing so everybody's clear about that, what the definitions are, what the current approaches were to this problem or still are, and how that motivated our project, what got us going into the SuperSID project itself, and then a brief overview of the infrastructure of the project description, defining our objective, our goals, our tasks, data, and tools to give you a feel for it. Then we're going to move into the meat of the talk itself, the project results. And we've sort of organized this in terms of features. And in SuperSyd, our whole idea was to extract and use features that were not commonly used for speaker recognition. And this more or less parallels what we're talking about, going from acoustic features, which is the standard current approaches, extracting out things like prosodic features, pitch and durations and energy, phone-based features, word-based features, all the way up to conversational turns time-based features, and then some results on some simple fusing that we were able to do at the end of the workshop of bringing these all together and see if we have complementary information. And lastly, wrap up with some conclusions and future directions. So again, to resync, what we're working on here is extracting out information in the speech signal that is telling us who is speaking. And we're going to hear about many other things during this workshop. In the afternoon, you'll hear about speech recognition, extracting out the words that are being said. But we're primarily focusing out on extracting the level of information that's telling us who is speaking. So we're doing speaker recognition. Now, the general area of speaker recognition has several tasks that can be addressed, three of which I show here are the main ones. There's identification, where you want to associate an unknown voice to a set of known voices. There's verification or detection, where we're trying to say, is this unknown voice coming from this particular hypothesized speaker? Yes, no, and detection or decision. And then segmentation and clustering. The reason I outline these is I want to make it clear that what we're working on is the verification and detection task, and I'll describe that more fully later on about what we're doing. So we're not doing an in-way classification, instead it's the straight detection task. Now, the current structure that is used in almost all detection tasks, speaker recognition detection tasks, is a likelihood ratio decision. And basically what we're doing here is we have speech waveform coming in, we do some form of feature extractions that we think are conveying speaker information. We'll then have two models, one representing the speaker that we're trying to detect or verify is the person, and then we have another model that we want to have represent the alternative, because we're trying to say, is this the speaker or not the speaker? So we have two models involved here that our features are going to be scored against. Take the ratio of those two to give us out our decision statistic, which we compare to a threshold to decide to accept or reject. Now, it's pretty obvious what you would have for a speaker model, because I might have training data for that person. I train a model, but the background model is a little amorphous, and it's mainly modeled in two different ways. One way is you can use a single model representing speaker-independent speech. So it's just representing what these features look like for speech in general, not for a particular person. Or we can use a collection of what's called cohort speakers to represent the behavior of some imposter models. So this is the target model we're looking for. We might have a collection of imposter models, and we want to know how well he scores relative to a set of background scores. The reason I give you this structure here is you'll hear throughout the talk, we'll talk about various ways that we've used our background model in training a speaker model. So this structure is pretty much a structure that we applied in all our different types of features and classifiers. Now, the current state of the art, again, hanging back to this structure, is for text-independent speaker detection systems is to use Kepstrel features and Gaussian mixture models for the models themselves. So the Kepstrel features are the features that we're extracting out. And for those familiar with speech, basically what we're doing is just extracting out information that's telling us something about the spectra at short time slices, 20 millisecond chunks of speech. So we have windows of speech, we do something with Fourier transform, and basically get a sequence of vectors that's telling us how the spectra is evolving over time. We then just model the distributions of those Kepstrel or those acoustic features via a model which is called a Gaussian mixture model, which is nothing more than a weighted sum of Gaussians, where we have a weight and a set of Gaussians here for our target model, for our background model, take the likelihood ratio on our decision. So that's the current state of the art. Pretty straightforward, pretty simple, but focused primarily and almost exclusively on the low-level acoustic information about how the voice sounds or the spectra itself in the speech signal. But we know that the speech signal conveys more than just conveys information about the speaker more than just at the low level of how the voice sounds, the acoustics itself. In fact, you can kind of think of it as a hierarchy of cues of how speaker information is conveyed to the speech signal. So at the low level cues, which you might think of physical traits, it's telling us something about the acoustic aspect of the speech. How does it sound? Nasal, rough, voice, whatever's in the acoustics itself. Going up a level, perhaps, in some middle range might be things like prosodics, the rhythm, the speed, intonation, volume, which may be indicative of perhaps the person's personality type, Are they type A and speak fast? Do they speak slow? Perhaps dialect is related to this. Emotion and other things might be commingled into this, but we're really saying about information that's conveyed that's more germane to the speaker itself. And then perhaps at the highest level, which might be called the learned traits of the person, are things like the idiolect and pronunciation. Idiolect being the words that you use, your particular turns of phrase, things like that. And these might have roots in where a person was born, their education level, and things like that. Now, following this hierarchy of cues from the physical traits up to the learned traits, it generally follows a range of easy to automatically extract to difficult to automatically extract. And by difficult, I mean computationally expensive and perhaps a little ill-defined sometimes of what you want to extract. Down here, people and in the speech community has been looking at extracting out spectral information for years and years, and there's defined ways of doing that. But basically, the point I'm making here is that there's no exclusive speaker identity cues in the speech signal. There's no one thing, if we said if we had this, we would know who the speaker is. Instead, it's sort of spread all over the speech signal, primarily because of what I showed you on the first slide, that the speech signal is there to convey many different levels of information, the language, the words, and the speaker itself. But we know that humans, we believe humans successfully exploit these different levels, but we're not in our state-of-the-art systems. And as I pointed out, that the current systems rely just on those low-level acoustic features. And it gives us very good performance. Commercial systems are based on that. The state-of-the-art and the NIST evaluations are using those systems. Very good performance. But they also can be susceptible to things like acoustic corruptions, microphone variability, and noise being added, because it will corrupt the speech signal itself. As I always pointed out, there's other levels of information that we're just not using. We're really exploiting one and letting the rest of them go away. Or if we are using them, they're used in a very implicit manner and not explicitly being extracted out. So we know that they haven't been used, but they have the potential for high accuracy. So going into this workshop, it's not as if no one beforehand had tried to use other levels of information. In fact, there had been early work at SRI with Heck and Kamal Sanaz of trying to use pitch, prosodic-based features. Before that, people tried to use pitch and prosodics. And for the most part, by themselves, they didn't quite have the performance people were looking for, so they tended to try it, abandon it, and move on to something else. Not that it wasn't a good idea, but it wasn't the most bang for the buck. More recently, some work by George Doddington and then follow on by Walt Andrews, Joe Campbell, and Fred Weber, who was at Dragon, working with Barbara Peskin at the time, started looking at trying to use words and phone, idiolect and phone sequences. And they found for a particular task, which I'll describe momentarily, you're actually able to do some reasonable speaker recognition just based on the word sequence and just based on the phone sequence itself, going after that top level of information. So this spurred us on to say, well, let's really focus in on trying to use these levels of information. So our objective for the workshop was to analyze, characterize, extract, and apply high-level information to speaker recognition tasks. The main theme being here is that we wanted to ban low-level acoustic information, meaning the capture. In fact, we don't even have audio on the disc here. All we had was features that we extracted conveying what we believe the high-level information. I'll describe that in a second. Our goals going into the workshop were to extract and develop new features and classifiers exploiting these high levels of information. So first we have to figure out what we think is conveying this in the speech signal itself. How do we turn those into features that are parsimonious or convey just speaker recognition information and not commingled with other things? And how do we get a classifier which can succinctly model that information and give us good performance when we do our detection task? Secondly, we wanted to show, based on these, that we can improve performance relative to baselines using some established evaluation paradigms and data sets. So we have a NIST evaluation paradigm, which I'll describe in the next slide, and we had some baselines that we were showing, and we really wanted to say we want to extract these things and beat these baselines. That was another goal we had. And lastly, we wanted to demonstrate that the new features and classifiers that we extract out aren't just pulling out the same information again and again, that they are actually giving us complementary information, that we can fuse these together and actually gain as we hope to do. So again, to reiterate, our task for the workshop was text-independent speaker detection. Given a test utterance, given a model, are they from the same speaker? Yes, no. That's the decision you're doing. So we have a model that's going to be trained from in-conversation halves. I'll describe the data in a second. And then given the test utterance, we'll determine if they're the same speaker. We are focusing on the NIST extended data paradigm. So we have a defined paradigm that's been used in the NIST evaluations. This one is from 2001. It's also been applied, at least the evaluation setup, in 2002. The data set that we're focused on in this is switchboard 1 corpus, which is conversational telephone solutions coming from 520 speakers. So we had a lot of speakers to try to average over, with about 5,000 conversation halves that these speakers participated in. One thing that's a little different in the extended data task, as the name implies, is that we now have speaker models that are going to be trained on variable amounts of training data going from 1 conversation half, which is approximately about 2 minutes to 2.5 minutes, up to about 16 conversations, which can be as great as 60 minutes, so 45 minutes. The idea in this task was to say, all right, let's look at, given we have enough training data to extract rare events or events that aren't just going to show up in 1 conversation, can we extract those out? And this gives us a chance to do that by having a large number of conversations to train on, and also to look at the performance when we back off to maybe only 1 conversation. How do these techniques and features that we use scale with amounts of training data? So primarily be focusing on, in here, you'll see results primarily focused on 8 conversation training. Although we did run it on all of them, we were focused on 1 spoke so we could kind of keep moving ahead. And 8 conversations can give a lot of training data and enough data to give us some statistical significance. We're testing on complete conversation side halves, so it's about 2 minutes of test data. And to use the complete switchboard data, it turns out there's a 6-way cross-validation done on the switchboard database. The reason I mention this is you'll see some results when we talk about performance on splits 1 to 6. Basically, that just means the cross-validation run on things. Yep.
Is the 2 minutes, is that pure speech time, excluding the non-speech?
No, that is based on saying it's a 5-minute conversation, and approximately half the time, people tend to be at 50%. It's not based on pure time. Now, so we have our evaluation and our data. Let me tell you a bit about what you're going to see in terms of how we're presenting our performance results. So we're doing a detection task, so we have a trade-off of 2 errors. I can falsely say that the speech utterance in the model were from the same speaker, and they weren't. So that would be what we're calling a false accept. Or I can say that the 2 were not from the same speaker, and they were, which we're calling a miss. And basically, we can take and sweep out our threshold in this likelihood ratio detector that I described earlier on, and look at our trade-offs in the 2 types of errors as a function of threshold, and plot that out on what's called a DET, detection error trade-off curve, where we can see the performance trading off one type of error versus another. So we'll be showing plots here that have these DET curves, and the main thing to keep in mind here is we're really wanting to get to this corner. In fact, we want to get lower than that corner, 0, which is somewhere down here. But it's lower is better, and it kind of gives you the scaling. We will also be presenting kind of summary statistics called the equal error rate, which is not the best way to characterize a total DET, but gives you a feel of the performance, and it's where this 45-degree line intersects, where we have an equal errors of probability of false reject and probability of false accept. And so that times it's a nice summary way to present that. Now onto the infrastructure itself. Here's the data and tools that we had lined up. So we had a lot of pre-digested data here, and I mentioned we didn't want to have the acoustic signal primarily because it takes a long time to process, but more importantly and fundamentally, we did not want to spend our time extracting out new ways to do acoustic information. We wanted to get the other information. So we had things like word transcripts. We had a bevy of these, it turned out, going from manual transcripts from Mississippi State, which kind of gave us a nice baseline of what a transcriber writing down, no errors supposedly in that. We had ASR transcripts from a Dragon recognizer, which had approximately 20% word error rate on there. Very good recognition run on the switchboard 1. Turns out we had the SRI ASR output also, which implicitly came in some data, which I'll describe momentarily, which had about a 30% word error rate. And then we had a BBN's Biblos real-time system, which had about a 50% word error rate. I just want to point out here, this was their real-time system run with no bells and whistles that was used for the 2001 NIST evaluations to give us development data and work on. So this is really a case of just running it through the system. So this in no means tries to compare the different systems themselves. It's just telling what we have. But what's important here is, what I think is interesting, I'll show results, is we go from perfect manual and we kind of look at the effect of degradations of ASR on some results, perhaps like an idiolect itself. We also had open loop phone transcriptions. So we had phone transcriptions running an open loop, no language model, just a bank of phone recognizers. One group is called the PPRLM because it comes from a system called the Parallel Phone Recognition and Language Model System used for language ID at Lincoln Laboratory. And we had phoneme streams in English, German, Japanese, Mandarin, and Spanish, so several languages in there. We also had the access to the global phone set of phonemes, which had potentially up to 12 languages. There was about 6 languages that we had online here that we could for contrastive cases in there. You'll hear about that later on. Katrin Kirchhoff also gave us access to articulatory features that have been run on the whole switchboard one. Yeah.
You don't give any performance for the phone.
Bad and bad.
Or perfect and perfect.
Yeah, choose a number. You're right, we don't, it hasn't been really measured. And I'll get into a moment later on.
Can it even be measured, do you think?
No, there is no.
Yeah. Right. We get very philosophical. The main workhorse that we had here, that we obtained from SRI, who also actually had already started marking up the Switchboard 1 database with what we call episodic annotations, which is just a sub-piece of other annotations they had done on Switchboard 1 and extended it to the whole Switchboard 1 for us, was what we're calling the SRI database, you'll hear that referred to. And this was the real workhorse for some high-level information we wanted to use. They had ASR time-aligned, both for the Mississippi State transcripts and for their SRI output of the words, and they gave us the PONs too. So for every word, we had the time-aligned pronunciation from the dictionary aligned, so we had pronunciation phones labeled here. We had a bevy of pitch information, such as the raw, median, filtered, and what's called the stylized piecewise linear pitch mark tracks. So for the pitch tracks on voice segments, they had gone through and matched, fit it with a piecewise linear model. So we had segments of linear fit. That comes into play later on, but it was nice, a nice set of data to work with, along with the energy and many other parameters, exotic features that were derived from these and put into databases, which we exploited too. In terms of the tools, the main thing I want to show here is that we really tried to use a bunch of different classifiers. Because we were extracting out new features, we didn't necessarily want to get into saying, well, everything has to look like the way we were doing it before, and indeed it would not. So we had things such as a bag of n-gram classifier, and by that I mean it's not the standard language model toolkit classifier, it's unconditional probabilities of seeing token AB if it was bigrams, rather than probability of B given A. There's some more to say about that, but basically, n-gram classifier, we had the CMU, CU language model toolkit for a real toolkit of language modeling. Jerry actually implemented a very nice binary tree classifier, which has some twists on it. It's not a standard one. I'll get into details on that later, which is good. We, of course, had to bring in a GMM classifier, because what would it be otherwise? We are using it. We had some discrete HMM classifier, which I pulled actually from the University of Maryland for some work that Andre is doing, and he'll talk about in the second part of this work. We had a multi-layer perceptron fusion tool that I brought from Lincoln based on the LinkNet toolkit to allow us to use perceptrons for fusing the information together. And then, of course, we had general debt scoring and plotting routines so that everybody was supposed to be NIST evaluation, and we could evaluate in the same way and present our results in a coherent fashion.
Sorry, Doug, what are the Kirchhoff tools? What were those Kirchhoff tools?
They're not tools, they're articulatory features.
I'm sorry, what are the features? I'm sorry. What are they all-
Katrin here?
What's the question?
What's the features?
What are the features? The features for characteristics of articulation, like place of articulation, manner of articulation, voicing, causality, and so on.
Good. All right, so we go to the preliminary. We know what the task is. We know why we motivated the thing. We have our data, and we've gone through. Now let's get to the meat of the thing. What are our project results? And again, remember, we're going following that hierarchy of low to high, and then pulling it all together at the end. So let's first get away with the bad news of, well, what were we going up against? What were the acoustic system doing? And I say bad news in the sense that I told you it was doing really well. In fact, it is doing really well. This is the debt curve we just described before for splits 1 to 6, looking at performance from 1 conversation up to 16 conversations. This is just reminding you of using Gaussian mixture models for a target and background and using Kepler feature vectors to extract. And here's our summary statistics. Basically, from 1 conversation down to 16 conversations, we're going from 3.3% equal error rate to 0.7% equal error rate. So in this data set, we had very low error rates to go with. Let me point out a couple of things. Why did we go with this? We went with this because we had a bevy of this alternative marked data from the SRI database and everything else. So we really wanted to stick with something we had all pre-marked up. Also, it sort of set a challenge. We wanted to know, could we even get to this level? But could we fuse with this? This is pretty low error. So can we use these high-level information to correct these things that the GM system just can't deal with? We'll get into that later. The other point I want to make, in addition to just showing you this, is, as I mentioned, I'm going to highlight in red the equal error rates, mostly at the 8 conversations. If you note here, when you go from 8 to 16, you'll see they're about the same performance, which is odd considering we had gains in performance as we added more training data. That's actually an artifact of the cross-validation. It turns out there was not a lot of speakers that had 16 training conversations, so that's actually a very variable plot in here. This one actually has much more statistical significance. That's why we're focusing on the 8, and you'll see that throughout the rest of the talk. So getting into things that we extracted. So we went in pretty quick. This is some work with Andre. Said, well, let's establish some baselines. As I mentioned before, a lot of work before just used very simple distributions of pitch. Said, well, we want prosodics. We'll just do distributions of pitch just like we did distributions of Capstra. In fact, that's what we put together here. So our aim was to extract out pitch and energy distributions. So extract the high-level the features that we think are conveying things other than Capstra, but still apply our standard approach. And so we had one case where we put together a 512 Gaussian mixture model that was looking at the per-frame features of log pitch, log energy, and their deltas, plus minus 2 frames around that. And we had a single background model for doing our light ratio detector. We also extracted out what's called a log normal tide mixture model of the pitch distributions from the SRI database. And in essence, what that model was, you have a center distribution, a Gaussian, that represents the mean pitch, and you have the probability of that it's the mean pitch. But we know that pitch extractors, and in fact sometimes due to speakers themselves, there's doubling and halving in pitch extraction. So you'll get a mean pitch, and sometimes it'll just cut in half or double itself. So the SRI database, they had modeled the integral pitch distribution, and then did a tide mixture model where they had a model representing halving and doubling of that mean value, with probabilities estimated of probability of halving given the model, probability of integral pitch, probability of doubling. So it's just another model laid on top that's trying to take into account doubling and halving. And one of the thoughts might have been that perhaps this doubling, integral, and half probabilities are conveying information about the person themselves. Did they break this, the pitch extractor, or are there things like diplephonia that's coming into play and used here? So here's the results. Equal error rate using the Gaussian mixture model. We had about 16% equal error rate on 8 conversations training on splits 1 to 6. That seems to be in line, again, given more training data, with what the literature shows, that you get about 20 to 30% equal error rate just using pitch. This actually had, pitch and energy in there, which was actually a gain. Using this tide mixture, it's 23%, and it's not necessarily unsurprising considering just the model itself, the degrees of freedom that are in there. So again, I don't want to dwell too much. This is more establishing baselines of just distributional approaches. So now let's get into extracting things that are not just the distributional approaches. And this is some work that you're going to hear more about later from Andre in the second part of the talk. I just want to summarize what he did, put it in the context of everything else. So the aim here was to try to extract out pitch and energy gestures. And this comes from a suggestion from Jack Godfrey, one of our remote associates, about that there might be these pitch and energy gestures that when pitch is rising, energy is falling, and a person does that characteristically at some part in their speech and they do it enough that it sort of represents some gesture itself. So that was motivating them. So our approach was to model the pitch and energy track dynamics. So not the distributions of the values, not the mean values, but what these two tracks are doing as a function of time. And as I mentioned before, in the SRI database, we had these stylized, piecewise linear pitch tracks. So we thought that was a good starting point to go with. So basically, this is how we, Andre actually modeled the dynamics, if you will, of these gestures. Was we had these piecewise linear fit to the pitch track. For each of these pitch track linear fits, he also then did a linear fit to the energy track and turned it into a very simple token. What was the slope? Quantized to positive slope, plus plus, and then a duration label on it. He'll also go into more details on this later, again, in much more detail later. But this is the way that we converted from pitch energy to a single stream of tokens. and then decided to feed that into a sequence analysis using n-grams. So we just modeled the bigram distributions of this sequence of symbols that are flowing in, and did our likelihood ratio between the bigram for a target speaker and bigram for a background speaker for this sequence. And here's some interesting results we had. The bottom line was we had about 14%, 13.8% pitch and energy slopes with duration tags. And what's really interesting on this is we're not using absolute pitch values at all, the distribution. This is purely saying plus, 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 minus, not where it was, but how it was moving in time with durations on there. If you recall the GMM pitch, which was really focused on the means and where they're distributing themselves with 16%, when we fuse the two together, the hypothesis would be that they should be complementary and add, because they're modeling different aspects of the pitch and energy. And indeed they do. We get a 9% equal error rate. That's pretty much what I'm just showing here on the plot. Taking two systems that were somewhat comparable but higher error rates, and they seem to be filling in the gaps nicely to give us a 9% equal error rate. Now, the next set of data that we wanted to look at in terms of the prosodics, or that we did look at, was what we're calling conversation size prosodic statistics. As I mentioned, in the SRI database, there was a boatload of statistics they had derived for us on conversation size. So for conversation 2143A, they would give you the mean log pitch, the durations of unvoiced, a lot of information itself. Barbara went through and extracted more, expanded that list from some other raw features in the SRI database to sort of give us two broad classes of duration-related parameters, features, and pitch-related features. And so the duration-related have to do with frames per word and rates and so forth like that, and pauses and such. And pitch-related have to do with mean pitch, max, min, over words and over conversation size themselves, and pitch slope. So they had two broad categories themselves. And we had these features, 19 in all, it turns out, for each conversation side. The classifier we used in this case was saying, well, that's just a vector. There's a mean and standard deviation associated with most of these. So it's kind of a vector of distributions, if you will. So I get two vectors of distributions for two conversation sides, do a symmetric KL distance between the two, and then I can put that into a k-nearest neighbor classifier. So during training, if I have 8 conversations, that's 8 vectors in my training set. A test enters comes in, I just find the k-nearest neighbors using KL distance, symmetric KL distance, and keep the k best of those as my target distance. Do the same thing for a set of background speakers, in this case using cohorts, and get a likelihood ratio statistic. So here's the performance of the individual features, again, broken out by pitch-related and duration-related features. This is on splits 1 to 3, 8 conversations for k equals 1. And we find equal error rates are going between 19 to 40% broken down. In general, there seems to be a trend, except for some run of things here, that the pitch-related individual features seem to be doing better than the duration. Not necessarily unsurprising based on prior information that we had. However, when we now fuse these together, so we take all the blues and run them through a fusion, whether it's a MLP or perceptron fusion or linear weighting of scores that Barbara did, these are the 11 duration ones, we get slightly above 14, maybe about 15%. And we get comparable results when we fuse together the pitch-related features. So now these are sort of equalized. So based on the individual features we're seeing collectively, they seem to do about the same performance. But again, when we fuse these two together, which we believe are modeling different aspects, pitch and duration type things, we indeed get a performance improvement. In fact, drop down to 8% equal error rate, just using these raw per side aggregated 19 distributions themselves. So that was a very nice push to use the prosodic information. So now, what I want to do at this point is I'm going to hand it over to Radu, who's going to talk a bit about the work that he did this summer. He and I worked together on this, but he was primarily the driver on doing some pitch-related matching of using DTWs on a per-word basis. This is really interesting work. He's going to go through that and the results that he was able to come up with.
Okay, so the origins of this idea lie in text-dependent speaker recognition, which basically means that the speaker gets prompted to say a phrase, and then after getting that phrase, they run what is called the dynamic time warping algorithm on the utterance of that phrase to match the pitch tracks and see how this speaker relates to the hypothesized speaker model. And We try to implement the same technique in text-independent speaker recognition, but of course the problem is we don't have a given phrase that we can compare for all speakers. So then what we try to do is extract single words out of the transcripts. I've only used manual transcripts for this. Not all the results are based on manual transcripts. And basically, you get the pitch track for each word and use the DTW to compare pairs of utterances of the same word. And what we hope to capture with this is stuff like intonation and accents and stuff like that. But the problems are that obviously this is highly dependent upon context, because a word can occur in different contexts and depends. Like it all depends on the place in the phrase or what the speaker is trying to say. There are also things like accent, which can hopefully that will discriminate between speakers without having to depend on place in the phrase, but it's still a problem. And of course we have the accuracy of the pitch data. We have having or doubling can occur very often on the switchboard 1. And in this first experiment I didn't do anything to account for that. If it was half or doubled, the hope was that the DTW match was too bad to take that word into account. So the outline of the algorithm is basically you have two word utterances, and you have a sequence of pitch values for each frame. And if you just lay them out, one on the vertical line, one on the horizontal line, you get basically a grid search. And each point on the grid corresponds to a pair of frames, one in the object utterance, one in the reference utterance, and you get a distance function for that position. And basically you need to get from the lower left-hand corner to the upper right-hand corner is basically the start and the end of the words. And hopefully you will get, you try to get a minimum distance path. And at the end you add up the distances on that path and you use some sort of normalizing scheme to account for variable length of the word and stuff like that. So basically you just get a mean distance across the path. So there are, of course, a lot of settings you have to implement, like you have to constrain the path somehow so that it doesn't stray too far off. Because if you just go on the boundary of the grid, you're going to match one frame in the reference model to all the frames in the object model and the other way around. So you don't want to, obviously you don't want to do that. So you have a global constraint like like the first one, which basically is represented by these lines. You cannot go past these two lines when you do the grid search. You have a local constraint which says, you can't go 3 steps to horizontally without going 1 diagonally, which means you cannot map more than 3 frames in the reference to only 1 frame in the object, or the other way around. This 3 is based on, it's just an ad hoc setting because the runtime was so huge that we didn't get a chance to tune that. Usually for text dependent they use 2, but of course being a text constrained model, the word utterances were a lot closer in length. So we used something slightly higher, because if you make that constraint too tight, then if one word is 4 times longer than the other one, you're never going to be able to reach the upper right-hand corner. So you don't want to get too many out-of-bounds flags and get too little words to look at. And there are issues like normalization. What type of normalization will you use? The most common one, the most efficient one, turns out to be symmetric normalization, which basically says that after you get a score for the path, you divide by the sum of the length of the object and the reference. The distance function we used is just the absolute value of the difference between the 2 pitch values. And that has the disadvantage that, for unvoiced frames, what we have on our transcripts is just a value of 0, and we treat that as 0. We don't treat it as a flag. We don't have like special case scenario for 0. We just take 0 as it is and use it as it is. And the hope again is that at some point you match a voiced frame with an unvoiced frame. The difference between your average pitch is like 100 something. The difference is going to be 100 something, so that will push your score away. And when you do a trimmed average on the scores, that will keep it out of what you're looking at. And the final score that we used was when you get the path score, you divide by the normalization. We used that initially, but then we thought we took the log of that and improved performance by 1.5% absolutely, so we stuck with that. Some of you are going to recognize this slide from Doug's talks over the past few weeks. This is just a basic outline of the experiment setup. So you have a list of words, we have 15 words in the end, and you collect all utterances of each word in the conversation you look at. You run them to a DTW match. You can do the same for the background. You normalize the score you get by the background, and finally you output a score. Obviously the DTW smaller is better, but in the end you take the negative of that so that you can fit the framework for everything else. So the word list was those 15 words. For our first experiments, we only had the first 5, then we added 5 more, and that improved by about 3% absolute, and then we added 5 more, and that gave us about 1.5% absolute better. Notice we have 2 word tokens in there, which are basically conversation markers, and the hope is that those are not variable upon context. And if people are so accustomed to saying that particular conversation marker, they will say it in the same fashion, at all times, not depending on context. Of course, the problem is that for words like true and well and things like that, they will not only occur as backchannel words or conversation markers, they will also occur in context. And again, we hope that by doing a trimmed average, we will throw those away. Okay, so that's roughly about 5% of all word tokens. So that's a very rough figure, but it's in that. It's below 10%, it's about 2%, something like that. But that also means that we have to do a lot of computation. For just to train the speaker model, we have about 8,000 DTW matches we have to do on average, and to get the background model, we usually have anywhere between 30,000 and 90,000 DTW matches. So it's a lot of computation, and it takes a long time to do it. So that's why we didn't get to tweak with all those settings. The internal DTWs were just ad hoc settings that we left with, and then all the main work was done on the post-processing and the scoring setup. So the scoring is for each word utterance, you take, in the test conversation, you take the best 15% matches of all the utterances of the same word in the candidate model. And you do the same for all the speakers in the background set. And the background set is 20 male and 20 female speakers, each with 8 conversation halves. Because we had so much computation to do, we limited the number of utterances we were looking at in the background conversations to only 3 per word. And that still gave us, 30,000 to 90,000, so it's a lot of words. And based on the background set, we just, based on those first trimmed averages, we just do an average on that, and we implement a decision on the gender of the test conversation, which is about 6% equal error rate. We're not, error rate, sorry, it's not using any state-of-the-art gender detectors, it's just the data we have, it's entirely self-contained. So that's 6%, and having found the gender of the test conversation, we normalize the scores for the candidate model by the scores for the background model for each word utterance in the testing conversation, and then for each word we average all the test utterances, and finally we average across words weighted by the number of utterances in the testing conversation. So basically, it's just averaging the scores for all the word utterances in the testing conversation. It doesn't really look at, this is this word, this is this word, but that's just the final result because we did a lot of grid searching on the scoring schemes, and those were decoupled initially, but it turns out that that's the best thing to do. And finally, the negative of the final average is the output support for the candidate model. And we only had time to do splits 1 through 3, so that's why this is not going to appear in the fusion with all the other models. We used 8 training conversations, and we used median pitch. We used raw pitch initially, but when we switched to median, it gave consistent improvement. And I did a few runs on 4 conversations on split 1, and it's usually about 2 or 3% worse than 8 conversations. And the equal error rate, we started out with around 30%, and we got down to 13.1. It's actually around 11 on split 1, which is the easy split. And that's the split that we did all our training on, and this is final figures. That's it.
I have a question. In a typical test conversation side, how many of these words do you run into?
It depends. It can be, well, usually words like well or aha, things like that can occur up to 20 times. Words like absolutely, which we just kind of threw in there because it was in the list of back channel words, and we needed a long one, and we needed to make it 15 instead of 14, so that occurs like on average like 0.3 times in a conversation. But usually I would say it's around 150 words per conversations we have. Yep.
So this brings up, building on Sanjeev's question, how many words in a conversation? I thought it was a few hundred.
I don't know.
You know, Roger, what the word count?
It's a few hundred. And you
Right, I didn't really look at the number.
But we're dealing with only 5% of those.
Yeah, I did a rough statistic on the whole switchboard one, and I got a count of all of these words and all total number of words on switchboard one. I don't really know that.
So what does the 5% mean?
5% means,
Frequency or?
sorry?
5% of all the words?
Of all the words.
Total frequency. 5% of the total frequency.
Yeah,
Of all the words in the conversations,
in all conversation on switchboard one.
the whole thing?
Yeah.
So you're talking about a few dozen words.
So what happened?
Maybe. I think it's definitely over 40, 50 for most conversations. And
So that it's more
it might be, yeah, it might
more
be.
than 5%.
Again, I'm not very familiar with the number of words.
But then you're taking 15% of those.
Sorry?
And then you're taking about 15% of those.
What's a trimmed average of the best 15 scores?
Yeah.
15% of all the match scores.
So if for a test utterance, you get a list of match scores for all the utterances in the target model, and then you take 15% of those. So you do a trimmed average on all the scores for a given test utterance across the target model utterances. So those will be 8 conversations, so there are a lot more
Across
than
the
that.
target, okay, I understand.
So what happens if the speaker never says any of the key?
That didn't happen in any of the conversations I looked at, but
You shouldn't.
I just don't
So
know
everybody
the
gets
score. I don't make a decision if that happens.
No?
I'm going to say we should play a game of taboo. Speak for 5 minutes without saying any of those words.
Right, one of the things I mentioned at the beginning, I just want to reiterate, so Radha was one of the undergrads that was working with us this summer, and although he didn't mention it here, I mean, this is kind of the tip of the iceberg as it is with all the stuff we're presenting. He started out early on with this, and somewhere about up here, and I set him a goal. I said, you got to hit 10. 10% is where you're going with this. And he was pushing it down, and every time he would chip away a bit at a time, but the system was kind of converted to it, so I think he did a great job in presenting this as all. And we are actually going to fuse this in later. At this point, it was on the 3 splits, but we're going to see if this helps with other types of information we have. So that sort of wraps up our prosodic features, or at least the highlights of our prosodic features themselves. Yeah.
A quick question. So this work was on the manual transcript, right?
That is right, the word.
Now for the other results, the prosodic features that you presented, what was the data there?
Barbara?
So I only worked with the human transcripts. That's all I've got to, and I think Andre worked with the
Right, so Andre's work, he has contrasted results between the two, the manual to the ASR. We tried to do that for the most case when we had enough time to go through.
general, very, very little degradation in these sorts of features when you need to do everything.
So let's move now into the next level up, into the phone features, or highlights from phone feature work that we've done. So the first one is more or less a baseline. I say baseline in the sense that this was developed before the workshop by Walt Andrews and Joe Campbell and other people, and Tina Kohler at the DoD, and they've been working on this for a while. And the idea here is that we want to learn speaker-dependent pronunciation using open-loop phone streams. That's what we want to do. Whether we're doing that or not is debatable, and we can get into that later. And our approach was to apply in-gram modeling to multiple open-loop phone streams. And again, in our case, we're using unconditional probabilities for bigram tokens, probability of A, B, rather than probability of B given A. And so, of course, what we have is the speech coming in. We have our phone tokens here. Our open loop recognizes in various languages. And we then have the models with the likelihood ratios for these streams independent of each other, and do a form of fusion at the end, which primarily is either just linear combination, maybe a perceptron, and get out our single score at the end. Most of the experiments that was done on this were conducted using the PPRLM phones, which came from the Lincoln LIDS system. And those had gender-dependent phone models, which actually did their recognition, so it was gender-dependent on there. Although I show 6 here, it turns out there was only 5 languages that were available for the gender-dependent languages. Hindi wasn't available, so those are the 5 that you see popping up again and again if you talk about a few of the streams. There's always these issues of how to deal with sparse data when you're dealing with n-grams. And so this used a form of pruning on here. This, again, wasn't a language model toolkit at the time, so it had some very rudimentary pieces that were put in place in our scripts. And then I eventually did a linear combination. So these are the results for splits 1 to 6 for the 1 to up to 16 conversations. Again, I'll just point out, highlight the 8 conversations. We're down to 4.8% equal error rate, just using the fusion of the phone streams themselves, the 5 phone streams, linear combination. Another interesting part to note on this is how, I guess you might say, non-robust it is to amount of training data. So here we are, about 5% equal error rate for the 8 conversations. But you see, with dramatic jumps, and at one conversation, it's actually performance is relatively high. So we're getting really big gains as we add in more data, which might actually point to some issues of smoothing and other things that we're starting to address now. Again, our main focus was on the 8. We're now looping back to deal with some of these. But having this in mind, and based on other things that were going on, Jerry started looking into using binary trees. And it turned out, I'll forward reference, that it helped with some smoothing issues later on. But the idea in the binary tree was we wanted to be able to build in more context than what we could do computationally with standard n-gram analysis with the toolkits, or at least with our scripts at the time. So with the n-grams, you tend to get local neighborhoods of 2, you go to 3, but then it kind of starts blowing up because it has to keep counts of all possible n-grams that are in there. What the binary tree does is allow us to actually have longer span time without the exponential explosion of the model size and computation. So for those not familiar, basically the way it works is we have the model token, or the token that we're trying to predict or represent, and we have some context, which are called predictors in this case. And here we might have these just back in time, so this would be perhaps one phone stream. And the binary tree pretty much just is a series of questions and trying to send this token down to the bottom where we finally have a discrete distribution of the probability of A given the path that it came down. So we want to ultimately get a probability of observing this given the tree. And each question is pretty much asking, is one of these predictors perhaps in a set? So it learns these questions here and starts sending its training data down and build up distributions. And that's how we end up propagating. And we can have this deal with larger context because each question might ask something about predictors way back in time. And I think we went up to about 3 predictors in time, which would be equivalent to about 4 grams. We can go up to 7. This also has some computation limitations too. Now, one thing different than the standard n-gram, which is pretty much just set the n-grams, do counts, and just go with that as it stands, is that this actually has an objective function for training the tree. And this is the brief description of how the training is done as Jerry implemented it. And the idea was that we wanted to build a structure that minimizes the overall entropy, prediction entropy, which can be equated to maximizing the likelihood of the training data. So again, given the training data, we had this model structure, giving a model that maximizes the likelihood of this structure given this data. And the way it works is It's basically taking the data and then going through all possible questions that it could ask given the token and the set of predictors that you've given it. Let's say you give it a context of 3 or 4, and it looks at all questions it could have, such as, is A at t-2 a set of this or a set of this? And starts going through those and trying to find out what an iterative way of going through and trying to see what the question is that will actually minimize the entropy in splitting the data. Once he has a candidate question, then he actually runs through and does a cross-evaluation on some held-out data. So find the best question, now run through an evaluation on held-out data or a subset that he's holding to the side to see if there actually was the entropy reduction of this data that's kind of propagating along with the tree as you're building it. There's also some occupancy constraints to know when to stop and build a leaf node, such as when if splitting the data would produce too sparse of a distribution or counts in the final leaf distribution, it stops at that point. Now, this structure ended up allowing a few things, 2 of which I'll describe here. One is it allowed us to do a form of tree model adaptation that Jerry looked into. And both these kind of came out of stability and smoothing issues that we started noticing that come out of training data. So in the tree model adaptation, one of the things he found was that when he tried to train this tree, again, just splitting the data and trying to build these questions on, let's say, 1 or 2 conversations, it was a case a lot of times that A, no tree would be built at all. It would not be able to split the data to minimize the entropy and just stick with a root node. Or you would get very sparse or shallow trees or other types of problems, which is indicative of lack of training data. So the idea here was build the training data using a large set of speaker-independent data. So learn the structure using a large amount of data that you know you'd have enough to train. So that builds the whole tree as the way we talked about in a speaker-independent fashion. You take that structure now, and given a person's training data, you propagate his training data through the fixed questions on the tree and basically update or adapt the leaf distributions based on how the training data falls through. So we sort of get the stability of a background training data with the updating of the given speaker's training data, whether it's a small amount or a large amount, and it's smooth between the two. The other thing to look into is sort of a recursive bottom-up smoothing. So as I mentioned, sometimes when you train, whether mostly not in this adaptation approach, but when you're training a tree just normally, you can end up with distributions down here that have sparse counts for getting these probabilities. So a back-off strategy would actually be to say if there's too few here, you can back off or you can smooth this distribution with the distribution of the parent node, which is obtained by actually just fusing these back together. And then that can be smoothed with the parent node and so forth and so on. So you can basically a back off going up the tree where you have more and more aggregated data, and you can do a weighted linear combination between parent node distributions and these leaf nodes to try to fill in the holes where you had sparse data. So these were 2 robustness things that Jerry put in. And it did give him gains, about 25% relative gain for the recursive smoothing and 20% for the tree model adaptation. Well, I think this experiment actually points out the robustness that's coming in more so than the 20% and 25%. So what we showed here are equal error rate as a function of training combinations, 1 to 16 going the other order. We have 3 systems here. The first one's the bigram, which I already showed you the performance for equal error rate. And again, it's a pretty high error rate at 1 conversation and works its way down when we get to the 8 conversations. Here's the standard binary tree with no adaptation or smoothing that's been applied to it. And we see here that it has the same problems at the low number of conversations, that the error rate's pretty high and some anomalous behavior actually at 2, but then works its way down and in fact does better than the Ingram approach at the 8 conversations. But note here on the adaptive binary tree that it also has worse performance at 1, but it's much better than this because it's able to use the stability of the background tree that was trained with a lot of training data. In fact, it's this much better robustness profile in terms of this error rate at the low number of conversations. And furthermore, it gives a better performance even at the 8 conversation, down to about 3.3% equal error rate. Now, another area of using phone features that we've looked into, so we've done the Ngrams, which are coming in baseline, the binary tree with back off, which another approach came through. And this is some work that Shin, one of the grad students in our group, was working on, and she'll be describing it in more detail again after the break, was to look at cross-stream phone modeling. So the idea is that we want to exploit cross-stream information from the multiple phone streams. And our approach is going to be applying the Ngram modeling to the cross-stream token. So to make it a little clearer, if we have the sequence of phone tokens here coming from English, German, Spanish, Japanese, what we've been doing is actually just modeling it in the temporal dimension, getting the bigram probabilities from this stream going here. But what she was interested in is saying, how can we tie these together? So one simple approach, which again was the outcome of several experiments, was saying, what if we did Ngram analysis across here? If we learned co-occurrences of when this produces something, what does this stream produce, and so forth. So she ran several experiments which you'll go into, one of which I'll show some results here is where she took these vector of aligned phone streams coming up from the 5 phone streams that we have available, and basically permuted it so she could look at all possible combinations in there, treat that as an observation, do the same for the next, stack those together, and now basically do Ngram on that. So there's no temporal information used, and this is sort of the unwrapping. Originally we had these in some arbitrary order, so if you did bigrams on this, you're arbitrarily going to have English tokens next to German, but if you permute it through all possible permutations, now you can look at all possible ways that they could have been put in there, and that's what she did, and basically do Ngram on that. I'll show the results next. One of the things that comes out when you're using phone information for these streams themselves is that, well, what is it capturing? Well, one of the things it might be capturing is, or one hypothesis going in this, is that the technique might be exploiting, in this case, speaker-dependent error patterns on the different phone streams. So we have the different phone streams, all of which were produced from the same speech coming in, but they might have different error patterns for the particular speaker itself. So when this one produces an A, this one produces something else, and it has different twists on that as it's going through. Again, Chin will go into more detail in the experiments themselves, examining what's going on with this and extending it perhaps to using other types of streams to pull in this information. But here's the bottom line. It did 4% equal error rate. So no temporal information was used, just sequencing the 5 streams themselves, running bigrams on top of that, and was able to drive it down to 4% for the 8 conversations, which was very amazing at the time when we were looking at it. And as I mentioned, she'll be talking about generalizations on this, where we can go. Right now, this was using the tools we had at hand, and we'd like to push this a bit further. The next thing I want to talk about, which I think is the last thing under the phone features, again, this is some work from one of our grad students, David, from Charles University. Again, after the break, he'll be going into details on what he did and how he did it. He came into this workshop with an idea. When we had our May meetings, he said, I want to see if I can learn pronunciations. I hear you got the ASR phones, the prawns coming out, and you got these open loop. Can I do something to learn the pronunciations? Because he read up on the papers of the Ngram analysis. And he wanted to come into it using his own way. So what he basically was going to do is he wanted to line up the ASR prawns, the phones coming from the pronunciations, with these open loop, and then look at the conditional probabilities, the probability of seeing an open loop given an ASR phone. So in essence, this is what he did. In the SRI database, we had the ASR phones coming out, and again, they were pronunciations. So for the given word to, it's more or less a dictionary lookup and then alignment of the pronunciation phone stream for that word. He had these other ones. He went through and did a big alignment of these on a per frame level, primarily because that was the lowest atomic unit that he kind of pulled them down to and line them up. And then more or less just implemented this equation. Probability of an open loop phone given an ASR phone for a given speaker's data. And just by ratio of counts, the number of times you saw a pair occurring divided by the total number of times you saw the ASR token. So just that conditional probability. And then during scoring time, he has these probabilities for a speaker. He also trains one for a background speech in general. And then he basically just computes the likelihood of the observed open loop, an ASR phone sequence against the speaker and background model and does his likelihood ratio. He's using multiple phone streams, which he also does linear combination for fusing at the end. So he's getting a probability table for the English given that, German given that, Spanish given that. And he'll go into details of why he thinks this is working and the other things that are happening in here. But as you think about it, it's kind of cool in the sense that it might be saying, well, I thought according to the dictionary, just grab the word been. It's been, But if you're Joy, maybe you're Canadian, you say bean, and you learn that. It's "een" instead of the "n," and it writes that down. So maybe it's learning speaker-dependent pronunciations in there. Well, here's the bottom line, and this is actually really amazing. He got down to 2.3%, and as he pointed out when I was putting this up, he's actually down to about 2.1%, but this was 2 days ago, so I don't care. In fact, I think he's running it now. I told him to link the number here electronically, we'll update it. But this was actually quite remarkable. And I mean, it's a straightforward, pretty much there. We thought it was going to be a case of kind of coming in, the idea seemed cool, try it, and then see, well, what are we going to have to do to deal with these frame issues and everything else. But it did extremely well, and it had a pretty good robustness profile. It's about 17 on 1. It, of course, has the same issues with having lack of data, but it seemed to kind of gain pretty fast. He'll talk about extensions on this work and more details of experiments, which I believe most people might have questions on about what if you didn't use the ASR stream? What if you used another open loop? What if you did other things? He'll have those results in his his talk after the break. I will point out that he ran this both on the manual transcripts and the ASR. This is from the actual ASR SRI database. So it's all automatic, all reproducible. In fact, when he does it on the manual transcripts, he just told me this morning, I think it's down to 1.7% equal error rate for the 8 conversations. So I wanted to...
Excuse me, the manual transcriptions don't have phones associated with
Yes,
Yeah, they do.
they aligned it. They did a forced alignment of the
it.
Mississippi State.
Using whose forced alignment? SRI?
So that's right. That was the first database we had to work with. They took the manual, forced it, and then did their phone alignments.
Doug?
Yeah.
Yeah, a couple slides back on the phone features, the cross-stream phone modeling. I just want to know if the way that you shook up the language order with English, German, and Japanese, how is that not equivalent to the bag of n-grams? Putting them in different orders so that you're creating a new n-gram from having the language in a different order? Right, we have the arrow there, you were talking about that?
What's the question?
So how is that different from just having a bag of n-grams as opposed to creating that, what looks like a 6-gram?
Oh, no, this was to say, this isn't the model. This is to say, in other words, if I did n-gram analysis, let's say in this fixed order, I'm only going to learn, let's say bigrams, I'm only going to learn blue and red together. I'll never see blue and yellow following each other because of the arbitrary fixed order I gave it. What she did was basically permute this around so that you look at put everybody next to each other so that you could learn, when your n-gram ran on this stream, you would be able to see blue, red, blue, yellow, blue, green, and so forth and so on as it's going through. Does that answer your question? So this isn't the model. This is how we manipulated the data to run it through the model.
I get what you're saying.
And that's independent of doing anything in time?
No time. No time was harmed in this experiment. Again, this is more of a placeholder we wanted to put in. We didn't do a lot of work on using word n-grams, and this, as I mentioned early on, was sort of work that George had kind of pushed on and really sparked a lot of this focus on using phones and n-grams and high-level things, if you will. So we just applied it pretty much as it had been done before. It's idiolect work, which is you have the word stream flowing in, you get n-grams, mostly bigrams in this case, or only bigrams in this case. For the target speaker, for a set of background speech, do like the ratios on there. What I wanted to show here was not anything new that we did, was it the contrasted results. People often want to know, what's the degradation when you go from manual transcripts and your error rate increases on the ASR input that you're using on it. And this seems to indicate that it's not a horrible loss of form. So this is the manual one, which is slightly above 8%. And then we see as we add more and more errorful speech recognizers, 20%, 30%, and the 50%, that it sort of has a graceful degradation in there. We don't understand exactly why all the degradation might be occurring. One of the issues that we've talked about a lot, both with this one and actually address the question that Tom asked about error rates for the phone recognizers, is that we don't believe error is the key issue here, it's consistency. I don't care if you consistently label cat as dog, just keep doing it so that my n-gram learns that. So you can have a 100% error or more, and actually have a very good system. So error rate isn't the driver, it's consistency. On the other hand, if you consistently put out A all the time, that's not going to help me either. So it's that balancing act between consistency but still marking discrete tokens.
Has anyone ever measured the consistency of recognizers in this way?
I don't know about speech recognizers, and maybe someone can answer in the audience on that. For phone recognizers, I will say that Mark Zisman, when he was doing, he did language models for language ID. He did some things about cross-entropy between the tokens coming out and the true transcripts, and tried to measure it in some way using measures like that. I don't know if people have done it for speech recognition.
Like, so you retrain your classifier on each of the recognizer outputs for this experiment.
Yeah, these are all independent of each other.
Right. You have to try to train, say, on the manual transcripts and then just test it on the recognizer.
That's a good question. Yeah. Well, two things we have done. That's actually a good one to do the cross case. What if you had this and you went to these?
Right.
Is it going to fall apart? I don't know. That'd be interesting to see there. The other one would be fusing multiple. Are these giving us different information in there? If we actually used output from different speech recognizers and fused them at some point, would that give us performance improvements like we're seeing with having multiple phone recognizers running in parallel? I don't know. But we see the degradation, and in general, we get around 10% equal error rate. So this is actually pretty good performance, again, using just the words themselves. Now, at this point, I'm going to hand it over to Joy, another one of the undergraduates in our team, and who's primarily been focusing on what we're calling conversational features, and she'll motivate that. By conversation, we're popping up a level rather than just focusing on the speaker. We want to learn something about how it's interacting with the other person that they're conversing with, and they did a lot of experiments on this. Hand it over to you.
So the goal here was to use this to try to learn something about the speaker interaction style that would be useful for speaker ID. And for the most part, that involved using turn-based speakers. So each conversation has two sides, which are split into strictly alternating turns, where the turns are intervals. And the basic question is there information on the non-target conversation side that can help with target speaker detection? And before the workshop, we had some idea that there should be some useful information there, because just looking at pause engrams gives a 25% equal error rate, where a pause engram is looking at the length at the pause in between turns for the target turn, which is the same as the length of the non-target turns. So to start off with, we just sort of grabbed all the turn-based speakers that we could think of, 33 of them, things like the average phones per second, or phones per word, the length of the words or the silences, and so on, lots of features. And then we wanted to know which of those features to use. So first tried using LDA to transform the data, but it couldn't really work with these features, so we had to search individually. And just to show what the LDA did, in these plots, each color is a different speaker. So for our best not transformed features, you can see that you can separate out the different colors, but the LDA kind of mixed them all together for the best dimensions of the LDA, so it didn't really work. So after looking through them individually, we found that the best three turn-based features were the phones per second, the average F0, and the average energy. And we did some smoothing using linear interpolation between the turn features and the conversational average, and then tokenized it, tried both using a GMM and using CDF, and then did n-gram modeling. So here are the results of turn-based modeling. And this is another graph of the equal error rate versus the number of training conversations. And all three of them use the same features, the three best features, phones per second, average log F0, and average log energy. So the blue and the green line are almost the same. The difference is in the tokenizing, so the blue line uses GMM and the green line uses CDF. And in the n-gram software, so the blue line uses the CMU toolkit and the green line uses the bag of n-grams. And the best number there is for the blue line at 8 conversations, about 15%. And the red line is a little bit different because it uses information from the other side of the conversation. So it used bigrams conditioned on the other side, and using Jerry's binary tree. And it's a little bit worse than the others. So here it didn't look like information from the other side was useful.
Could you clarify, I mean, we've already discussed pitch and energy measures. How are these pitch and energy measures?
They're measured over turns instead of over words or over conversation.
In addition, there's this sequence modeling of it. So each turn was converted to a token via the quantization, and then you had a sequence of tokens. So you learned kind of this pattern followed by this pattern. So as opposed to the early stuff, I think Barbara early in the talk that Barbara did. There it was actually had distributions, and you actually did a real value distance function between two things, or GMM distribution. Here there was a quantization level trying to say how your patterns change from turn to turn.
Can I ask this question just because you were closest to the data? Did you notice any evidence of entrainment where people's pitches were pulled closer together during dialogue? No?
Excuse me, how did you define the turn boundaries? How did you find the turn boundaries?
They were labeled in the SRI data to be strictly alternating. So things like somebody says that
They were hand labeled?
Actually, I think, if I can correct that, I think that what was being used here was actually automatic turn labeling, and they're not really turns. So you look at the Mississippi State segmentations had chunks that were demarcated by sufficient lengths of silence. And I think what was counted as a turn here was you look at all the chunks and you order them by start time. For the two sides of the conversation combined, just sort by start time. And then do all the A's until you run into a B, and then do all the B's until you run into an A, and then do all the A's until you run into a B. So it was fully automatic, I believe. Well, modular Mississippi State
It was instant like tag, really.
Well, but then you merge segments until you run into the other guy.
Right.
So I think that's what counted as a turn.
Okay.
So then looked at word-based features as opposed to turn-based features. So the idea here was that maybe people change the how many times they say a certain word based on how many times the other side says a certain word. So if we just look at the distribution of words for the target side for some small list of common words, I got an equal error rate of about 23.5% as a baseline. And then I tried splitting the distribution up based on whether or not the other side says the word, for example, 0 times or 1 time or more than 1 times. And doing this, I wasn't able to beat the baseline equal error rate, trying different settings and so on. And one reason might be because even if I had 8 training conversations, the non-target speaker changes in each conversation, so you only have about 5 minutes of training for each non-target speaker, so maybe just not be enough time to change how you speak. Or maybe not picking the right words, or it only happens a few times for each word, or you really need timing information.
Questions? Great. Yeah, we sort of probably should have used ourselves to see how much we picked up each other's turns of phrase throughout the 6 weeks of working together. I know I picked up a few things that you catch yourself saying, why am I using that person's phrase all the time? So it may make more time, but this is interesting. All right, so we're in the home stretch. We've kind of given you the highlights of the different levels that we've pulled out, give you the pieces of them. Again, you'll get details on some of the real interesting work that the grad students have done after the break and a detailed breakdown of experiments. Now we're getting to the point of, okay, we have all the ingredients out. As Joe likes to say, can we make soup out of it now? So we went with a very straightforward way of combining these things. I just want to digress for just a second on this, that we're using a single layer perceptron. We don't believe this is the way things should be fused ultimately. This is the way it's currently being fused. But as you think about how you as a human goes about using different levels of information, the reality is you switch based on externals or other things dropping out. So how this should be fused is not the ultimate way. What we're doing is not the way we believe, but we believe it's a good going-in proposition. Then to start to look at further out things of how we can fuse these. But we wanted to at least show that we were getting complementary information from these different levels of information features that we were extracting out. So again, it was a single layer perceptron that we used from the LinkNet package with a nonlinearity on the output. So we feed our systems in, there's a bias node that's in there, and it basically learns these weights. These are fixed, and we get a probability of target and non-target coming out. The weights were trained using a lead one out cross-validation on the 6 splits. So the perceptron that was applied to split 1 was trained by taking the data from splits 2 to 6 and training it and then rotating through. This was done on 8 conversations, so it's not on all the conversation training, but it's focused on one training condition. We selected the best, and I say best in quotes, sort of a pull through of different things, individual systems to fuse, and we ended up with 9 of them. And I sort of show these in the categories the ways we've been describing and going through. We had, of course, our acoustic base, the GMM Keptra, on its own. We had pitch or prosodic-based things, such as the pitch and energy distributions, the K-nearest neighbor prosodics that Barbara worked on, and then this pitch energy slopes that I mentioned early on, with one addition on here that Andre will go into more details in his talk. They were actually tagged also with the phone information, where the slope, pitch and energy slope occurred under what phone. So this one actually sort of spans between prosodics and what we're calling phone-based things, such as the phone engrams, adaptive binary trees, the cross-phone engrams, and then the conditional ASR, open-loop conditional ASR. And then lastly, the orphan here of using the engrams on the words popping up the level. We did not get into the conversational turn information, primarily because it wasn't necessarily giving the performance at the level we wanted at the time. We were able to get it into the system. And now here's the bottom line. Splits 1 to 6, 8 conversations. 3 amazing results in here. 0.7% equal error rate for the GMM alone. Red line. Take all 9 systems, fuse them together. We're at 0.2% equal error rate. Take everything except the GMM Keptra. No acoustics allowed. We're at 0.7% equal error rate. So we're pretty much ready to go home, except that this just happened yesterday. So we kind of met our deadline on it. But this was amazing when we hit it. In fact, it was a progression. As we started fusing things early on, we started seeing some systems as they were fused started to give us less than 1% equal error rate. That was a magic number. Once we broke that, we said, this is amazing. How did we be able to break that with no acoustic information? And then these latest ones came out with some fusing stuff that Joe was running the other day. We were taking our systems and going through. So this sort of, we debated about just putting this up and walking away and a break in the morning. A little bit of analysis on it. We haven't gone into a great deal on it. Again, fusing, of course, is always the last thing that gets done because all the systems are being put in place. Here's the individual systems that went into the soup in order of their equal error rates. We had our GMM Keptra, of course, was giving us the best error rate. The GMM pitch was the worst. And then we had things like the next best was this conditional ASR around 2%, using the conditioning of the open loop given the ASR. Then there was a whole stream of these phone-based information. The binary tree of phones, cross phones, engrams on phones, the slope plus the phone information, as I said, one that kind of spanned between the two. The K-nearest neighbor on the prosodics, the engram on the word, and then of course the pitch. So the phones tended to do pretty well individually, things that use the phone information. So now we group them and fuse those individually to see, well, what would they do in somewhat of these arbitrary groupings of prosodic information only, phone information only, word information only. And that's what we show here. Acoustics only. These are all the phone systems that I described in the previous page. These are the prosodic systems with one caveat. We removed the system that Andre put together with slopes commingled with or conflated with the phone labels, primarily because it sort of spanned between the two. And having it involved in either one of these kind of took away and deflected away from the analysis of what we were trying to say is, what if it only used prosodic information? What if it only used phone? Again, only in the sense of what we believe is using, it might be bleeding in. The other caveat I'll put in is that this is sort of the redheaded stepchild of the workshop in the sense that no one really paid much attention to it and sat in the corner. So it's not as if a lot of work's been done on using word engrams and trying to really develop them as much as been done on the other things. So the fact that it's up here is a function of two things. One, there's only one system in here, there's many of these other ones. And two, there hasn't been a great deal of focus. We have ideas of what we want to do, but we had all these other ones that we were looking at. In fact, we had some experiments we ran on there that I'm happy to discuss offline. So that's the bottom line. And again, it's really amazing that the phone stuff is getting us as far as we're going, and the prosodics are close to the 6% equal error rate just on their own. Now we also did a little bit of analysis, try to say, well, what's the best systems in coupling it? So we're running this grid search of what's the best 2, the best 3, the best 4, and so forth, fusing together. So if you can only choose 3 and such, and we're still sort of running those. But here are the best 3 non-GMM CAP systems, so non-acoustic based systems, if you will, that if they've been fused together. So we looked at all possible ways of taking the non-acoustic based systems, non-Kepler based systems, and fusing them. These were the three that gave less than 1% equal error rate, the best, and broke the 1% equal error rate. And it consisted of this conditional ASR, the slope and foam tagging of the n-gram, and interestingly, it brought in the prosodics, the k-nearest neighbor, using the prosodics overall. And what was really interesting here is primarily based a lot on the two of them foam-based, but you can see it brought in the bridge one of the slope information, and it brought in the k-nearest neighbor of the prosodics. So it's really telling us that those being put together are helping us, and really going after what we had hoped to go for is getting complementary information that we can fuse together. So where do we go from here? A lot of things. We have a lot of questions that we have to answer and dig through and analyze what's happening, why things are working, what's the underlying structure, and can we relate that and actually improve upon it. So we need to look at perhaps enhanced modeling. So some of our modeling techniques, although we had a great deal to deal with, you notice there was some pushing a square peg into a round hole by forcing things into n-grams, or forcing them into there. So there's things like going to discrete H&Ms, or things that can do better, more sophisticated sequence modeling that we might want to look at, or variable length engrams. Better normalization techniques. We know that in the acoustic system, how you do normalization of the scores or the models themselves can have a big performance boost. And in fact, in the Kestrel system I showed here, all the bells and whistles were turned on. There was 2 levels of acoustic score normalization. On one level of acoustic normalization and one level of score normalization. So it wasn't a held-back system by any means for the Kestrel system. We want to look at new features to capture perhaps the speaking style. These turn-based is actually rather intriguing to us about how you adapt to the other person, or more generally, just what's your style, kind of this upper level thing. So we've had lower, still higher than the acoustics, but not as high as we'd like to go in getting a speaking style. Error analysis, we want to see where is this thing complementing each other. When is it filling the gaps? Under what conditions is it happening? Sort of robustness. And of course, the big looming challenge is on the switchboard too. As is clear, and we'll state up front, we've done this work, we've kind of shown that this information can be extracted and applied, but these experiments still have to be sort of labeled as development evaluation, because we were actually running and tuning on the data set itself. Not cheating, we had held up data and so forth, but we'd like to try this on the fresh data. Switchboard 2, run it on there. Part of the issue is getting all the markings and everything else that's available, but we view that as a real key challenge, doing on the Switchboard 2, and then perhaps on to other types of data, the meetings, the cross-channel, and beyond, to see, are these going to give us the promise of A, holding up on new data, and B, giving us the robustness that we'd like to get from using higher level information, which is the evaluation of robustness. You'll hear some proposals after the coffee break that actually focus on trying to look at and examine the robustness by adding noise and extracting out these high-level features to see if they are helping us under these cases. And then perhaps maybe moving on to other speaker recognition tasks themselves, not just detection, but perhaps segmentation or tracking type of tasks. So wrapping up, I think we accomplished most of the goals that we set out for ourselves. And no, we didn't write the goals after seeing what our results were. You can look at our opening slides, which are documented in there. So you can read through those. I mean, basically we wanted to pull out, and in fact this exceeded what we wanted, exceeded what we'd like to do. We thought when we got done, after trying to extract out all these different levels, we would have the pile of techniques laid out here and sort of say, well, this kind of helped and this helped, and close our eye and not look at the acoustic information scores and say, well, maybe we'll get there. We didn't really expect at all that fusing it together was going to give us the performance that we achieved on here, nor that fusing it was going to drop it on the acoustic information itself to the 0.2%. So we have actually had both things. We've shown that we believe we've shown that it's complementary information. We've pulled out many different levels of information, applied several types of classifiers and features to it, and was able to knock the baseline down. And so we're ready to move on to the other challenges. We believe that it is providing this wealth of new information that's untapped, but needs to be fused together with things in the right way, and that's what we're going to be looking at now, is trying to go on to fusing, we believe, is a big issue in there, and that it's giving us the complementary information. And then, of course, Super Sid. So I guess we have a few minutes for questions, or we can take an extended coffee break.
Also, I mean, whatever.
And see anybody in the Superman shirts for questions. Everybody knows what everybody did in this thing.
Back to the next question.
Yeah.
Oh, okay. Yeah. So I have one question about. So you had a very nice description of breakdown in terms of the level of information, whether you're using acoustic information or the higher level information. Did you look at which features used temporal dependencies versus which ones did not, and the relative performance of that based on that?
That's a good point. So most of the phones, of course, so all the phone things that were in there were using temporal, except for the cross phone. But we'll talk to that actually fused together. The GMM used no temporal information except for deltas that were in there. And
But is it crucial or not to use the temporal information?
right, I was trying to think in my mind of the things that were done. One point, the conditional probability that David did of the phone given ASR had no temporal information. It was just counts.
Excuse me, it most certainly did.
Yeah.
You have the context of the word.
I'm sorry.
If it's a forced alignment, then it's going to have temporal.
Good point. So actually I'll back off. If there was implicit alignment and other things that brought it into play.
So is that, I mean, in the fusion, is that complementary if information?
That's a good point we need to look at. I mean, I had thought of going along those dimensions of static versus temporal, how much that's bringing into it. Yeah.
What's the human performance on this test?
Well, if you have a couple of years, you can listen to the data and check. It's too big to do human performance on this, unfortunately, because it's training on about 45 minutes with 500 speakers, so I don't know. The only numbers we have, and actually,
It's right here.
we have some people that actually run some of the human evaluations on it. What was the numbers you were getting?
Well, excuse me, but I'm sorry, but that's not comparable. The experiments were not comparable.
Oh, they're not comparable. I'm saying that's the only one that's been done that I know of.
And that's, it was only on the 10 or 30 seconds and,
It was
So
on,
what is
it was on the, it was on
2
the
minute training,
2-minute training,
10 seconds.
10 seconds, maybe even 3 seconds.
Yeah, I mean, it's just not comparable. And it was only on.
Order of magnitude.
Oh, well, actually, I'll give you my I think it's 100% error for humans. Because no one's going to do it. No, and I'm being facetious. I don't mean, you're bringing up a good question. What is it? And you're right, unfortunately, we don't have that gold standard there. So I don't mean to minimize it, but unfortunately, it's just so hard to get it.
Is a question there? Why don't we go on?
Yeah.
Just which of these of your winning feature combination there, did any of them still have were still encumbered by the use of the manual transcripts in any way, or were they all based on totally automatic feed extraction?
So I haven't run mine on automatic yet, but it'd be easy to do.
This is the only one that use manual.
And that, a lot of those features are, their pitch, that's the zone function, the word alignments, the
So everything
boundaries,
else
averaging over
is the
features.
ASR. Alex?
This of course fantastic results, but at the same time, in the practical situation, you would have presumably another possibility for trying to apply speak IP systems to cross-channel situations and also cross-lingual situations. You mentioned that as well at the talk. Now, many of the features probably would not be applicable in those situations, and also the combinations and the robustness of each of them will differ quite dramatically. Did you do any experiments? Could you speculate how that might shake out? We do know it gets a lot worse unless anyone thinks the problem is solved.
Oh, no. I mean, the reality is absolutely. This is focused on one corpus, the switchboard one, the extended task, the cross-channel, all those things. This is more of an existence proof than saying it's the
We
solution.
find some of this and allow them to meeting data, and this is horrible because it depends so much on where the microphone is and things like that.
Right, and now the thing is, almost everybody's going to get hit by that. The acoustic systems too get hit by it, so it's not peculiar to particularly any of these. As for which ones might be more robust, I don't know at this point. I would suspect One of the things that's a little odd when I say this, we say the non-acoustic. The reality is everything's derived from the acoustics at one point or another. So how they derive and push, how they derive things and actually extract it out. I don't know. That's actually a big push we want to go to. Switchboard 2 actually is more errorful because of some handset variability that's not present in switchboard 1. And then the noise issue that I know Shin wants to look at and other people want to bring into play on it. But at this point, I really can't speculate because I don't know, but I can say and agree with you that it's going to degrade, perhaps dramatically. Tina?
Did you do any comparison of complexity with the acoustic versus these items to see how computing is going to impact this time?
Sure. So this is faster than real time, and when you fuse it all together, it's probably about 10,000 times real time. We joked about that. We thought about having kind of that, having the scales thrown out. Absolutely. I mean, you got ASR and phones and all these other ones running in. One of the things that helped us this summer was we had pre-digested data, so we didn't have to deal with all that at the time. So it actually ended up being turnaround time much faster because we'd already extracted everything. But when you have to go and extract it, that's going to be a heavy burden. So once we show that these things work, then we're going to probably have to do the engineering trick of trying to figure out how can you extract it in a less computationally intensive way. And in fact, there is work that David is looking at and other people are looking at it, even trying to move away from being tied to the ASR output. Rather than conditioning on the ASR prawns, what if you condition on an open loop or something else that's less expensive so you're not tied to that, so that producing these things won't be as computationally burdensome as you'd like.
But if I can just add to that, Tina, I mean, it depends really what your app is. So, for example, you might be in a situation where you want to know what the words are. You're running a speech recognizer anyway. You're extracting a lot of this stuff. Use it. Throw it into the speaker ID mix as well.
Well, I kind of have a feel for some of these, the code recognition and the ASR. The other ones I didn't specify.
Oh.
A lot of them just come from forced alignments of the ASR output. And so if you're running an ASR system, the forced alignment is epsilon more time than that. You just do a back trace and you have most of the data.
The fundamental feature actually beyond the ASR and the phone, which we said you have a feel for, actually is pitch and energy. And then a lot of these are derived from those conditioned on the
Yeah, I sort of want to go back to actually the first question, which had to do with temporal. How the GMM system doesn't require any language model in any way. How many of these systems that are working well don't require a language model? Are they more like the GMM with some sort of quantization into categories?
Right, this gets into kind of what Jeff's question was, the temporal versus non-temporal information, or language model being one of those. The phones, I mean, I don't know how to answer it. At some level, when you pop up, they actually brought in more temporal information itself. Language model-wise, the phones, these were open-loop phones, so the ASR had language models in it, of course, to do its...
So open-loop phones are like the GMM system, except there's a level of quantization in there.
Yeah, you can look at it that way. Right. There's a three-state, it forces some time to spend in that. But you're right, it's open-loop. What phone follow what phone, just let it go unconstrained.
I'd like you to take a break now so that we can stick to the schedule, and we'll be back in 10 minutes.
They're not terms.
We're now going to move into
But they're the best one.
the second part of the Superset presentation. So this portion of the presentation is actually where we're going to have the grad students come through and give their three proposals. We're going to have Shin start off. That's going to be followed by David and then Andre, who are the three grad students. They'll introduce a little bit about what they're doing. The purpose of these presentations are A, to kind of get a feel of what's happening, and B, to do a proposal for future work. So Shin will start.
I should say that we have some money from NSF to support further work of graduate students. And throughout today and tomorrow, you'll hear proposals from graduate students as to what they would like to do. And there is an independent panel here who are going to judge them and make a recommendation as to which ones we ought to support and which ones we ought not to support, or we don't have enough money to support.
Hi, my name is Qin Jing. I'm from Carnegie University. The title of my presentation is High-Level Phonetic Information for Speaker Recognition. Okay, so the aim of this work is try to model speaker pronunciation idiosyncrasy contained in the phonetic sequences. And the main approaches we used this summer are language modeling techniques. And some motivations behind this work is like some previous related work has shown that significant speaker information can be captured by using just a simple n-grams on the phone sequences. And also, our previous work shows the potential of language independence and robustness under different noise conditions of this approach. So, but the previous work focused only on modeling information in a time dimension. That means only explore the information contained in each single phone sequences. So the focus of my work this summer was try to examine modeling information not only in a time dimension but also in a we call cross-stream dimension. So the outline of my presentation is first I will describe the work of applying language modeling technique on the phonetic sequences. We call this phonetic language modeling in time dimension. And second, describe the work using this phonetic language modeling in cross-stream dimension. And then I will talk about the combination of information from both dimensions. And then I will discuss my proposal for future work and finally complete the presentation. Okay, so here is the explanation of the phonetic language modeling in time dimension. So again, the aim is try to capture some pronunciation idiosyncrasy contained in the phone sequences. And the approach we just apply the n-gram modeling to the phone sequences. So by sequences, we imply that they are time series. So that's what we mean in time dimension. So this graph shows the workflow. Like also, Doug has already shown a similar graph in his talk. It's basically like the speech, the phone recognizers from multiple languages decode the speech. Can be either from target speaker or background speakers, and output phone sequences. And the phonetic language model is built on these phone sequences. And then during the verification, the test phone sequences is scored against the speaker phonetic language model and also the background phonetic language model. And we compute this likelihood ratio scores. And these multiple language-dependent likelihood ratio scores are finally fused together to give the final decision score. So this is basically what we did before. And here it shows basically this is a baseline result. So we have two data sets. One is PPR and open loop phone streams from 5 languages. And then the other is CMU global phone, open loop phone streams from 6 languages, potentially have 12 languages, but this summer we used 6 languages. And we got a comparable experiment result on 2 data sets, but for simplicity and consistency in this slide and also in the following slides, I will only show the experimental result on the PPR open loop phone stream data set. So this is just bigram modeling using CMU language modeling toolkit. And this results are from ALL-SPACE 126 8 conversation training. So the idea of apply this phonetic language modeling in the cross-stream dimension is try to explore the information across different phone streams. And I tried a lot of things, but here I will only show one simple but working surprisingly well approach, which is I just learned the dependencies across multiple phone streams using this bigram modeling. So first, the multiple phone streams from multiple languages are aligned according to their smallest time overlap. So this figure showed how the alignment is done. Like basically the phones in each phone sequence, each language phone sequences is duplicated to the smallest time overlap. And I tried first like learn bigram dependencies on one fixed order of this aligned phone sequence, which is like just learn the dependencies of this. And then also try like learn bigrams dependencies on manipulated data like by permutation, and the hope is we want to learn the bigram dependencies between all pair of phone streams. And so there is no temporal information used here. And here shows the experimental result. Again, it's also on the PPR and open loop phone streams from like 5 languages, and results on all splits 1 to 6 and 8 conversation training. So the blue curve is the baseline I showed in the previous slide, and the black one is the cross stream just with one fixed order. So actually this one works surprisingly well, and comparing to like the red one is the cross stream with this kind of communication. And so from this these results we see, so both dimensions can capture some information about speaker. So can they do better if we combine the information from these 2 dimensions? Then the answer is yes. So I just tried a linear combination of the scores, like decision scores from the time dimension system and the cross-stream dimension system. So this is just both systems have just bigrams, and the equal average down to 3.6 compared to 8.4 in time dimension and 4.0 for cross-stream. And so what we learned here is both dimensions contains the important and somehow complementary information about the speaker. And the same thing is also the same result is like I also try to combine linear combination of the binary tree in time dimension. Remember, Doug described this binary tree. The binary tree can learn longer time span, the dependencies in longer time span in the time dimension, and fuse this with a cross stream, and the equal average down to 3.0 comparing to the previous result I showed, like just the 2 bigram dimension systems. So okay, so let's see what I did so far. Like we have this aligned multiple language phone streams, and in the time dimension we just model this bigram dependencies, and also in the cross-stream dimension we just manipulated this data and try to learn these dependencies across different phone stream pairs. And this is these models are just ad hoc models, and but in both dimensions, we can capture some information about the speaker. So we think the better modeling approach is desired to more efficiently capture the speaker information across in 2 dimensions, such as not only in the time dimension, but in the cross-stream dimension, but also both across time and across stream. So And looks like graphical models provide a general framework for capture information in both dimensions. So we can learn not only just single diagrams, but also longer time span dependencies in the time dimension, but also some dependencies across the stream. Also, it's possible we learn this, maybe there are some relationship, the dependencies, both across time and across stream, and we didn't explore that yet. So, graphical model provides such a framework that makes it possible to explore the information in both dimension and the mixed dimension. So also later on, if we can make the model structure compact, we can introduce hidden variables. So yeah, and so in concrete, this is my plan for the future work. First, I will locate suitable graphical model softwares for the task. And there are quite several already available graphical model softwares, such as GMTK, which is the product from last year's experiment workshop. And I'm starting to do some preliminary experiments using GMTK. And as I showed in previous slides, we start it with some, like, not randomly. We don't add these curves, these dependencies, like just imagined. We can use some criteria such as mutual information between all the, like, in the time dimension, in the cross-stream dimension, and both cross-stream and cross-time, and rank these mutual information relationships, and just pick some pairs that have strong dependencies and a curve there, a relationship there. And we start with this structure and try to learn the dependencies underneath. So I will first examine this using the current feature streams, like the multiple language phone strings. Start with this, and because we already have this simple linear combination to compare with, and what I also want to discover is what is the underlying structures of this model. The model has learned, because, like, we have tried some experiments using the binary tree to learn the dependencies across stream and across time. And binary tree did pick some strong relationship between some, like, either across stream or across time, but it may pick up just the dependencies inherent in the data, but not discriminate between speakers. So that maybe if the underlying structure learned is this, so we need to think about how to change the training criteria, not to just maximize the likelihood of the data, but also using some discriminative training strategy, try to maximize the discriminating between different speakers. So, and then I will extend this to other non-phone features. As also Doug mentioned, we discussed this, like what we did use these phone sequences right now. So it looks like we just use some non-perfect system, non-perfect phone recognizers, and try to, as Doug said, there are some error types of some related to speakers. And if in the future we have perfect phone recognizers, So there's no way we can do this to discriminate speakers. So that's why I want to, because this is a general framework that can be applied to other features such as articulatory features and other features that can be aligned into this multiple streams, such as this pitch, slope, cross waves, the features as Andrea will describe in his work. And then I will also look at the robustness of this modeling technique, such as robustness against different acoustic conditions, also robustness against languages. So our previous simple work showed the potential of this robustness, but we need to verify this. So in conclusion, this summer in the workshop I explored modeling speaker pronunciation accuracy in both the time dimension and the cross-stream dimension. And we found each dimension contains the speaker information. And this simple combination of both dimensions, it works much better than each single one. So that means we do need to find a suitable modeling technique to model this information in both dimensions simultaneously. And so I propose to study more general modeling technique and apply such as graphical models to apply to the phone streams and discover the underlying dependencies, and also explore using this modeling technique to the non-phone features and investigate the robustness. And so I will develop on the switchboard one what we have already the frame set up for the framework, and evaluated on switchboard 2, which has more difficult acoustic conditions, and use NIST extended dictas.
We can get some questions. I wanted to give each of the grad students enough time to go through their thing, so I just want to move on. We can again, if we have the time at the end, pose the questions to the individuals.
My name is David Kozacek. I'm from Charles University, and I did pronunciation modeling this summer. The purpose of this modeling was to try to figure out which phones people tend to use when they think they pronounce particular phoneme, because this could be speaker discriminative measure. And I took as the input 5 of the open loop recognizers. These were those English, German, Spanish, and Japan. And as phonemes, I took data from ASR SRI database, which were forced aligned to the recognizers out. So it looked something like that. This is word 2, ASR, and those open loop phone recognizers. These are just lying side by side using time information, which is in frames. And we have a good luck that the frames were the same size for both ASR and open loop, so no other processing has been done on it. Now, in the training phase of the model, let's concentrate on one stream only, for one stream open loop only, say the English one. We estimated probabilities of English scene E given ASR scene A just by simple counting per frame. And these probabilities were computed for both speaker and background model. Then in the testing, conventional likelihood ratio detector was used. So again, you can imagine this as being frame by frame, because this number of EA occurred is just the same as summing over the frames. And I should say that before any processing, that we removed data containing crosstalk, which were detected by Silence X phone in the open loop. And then the total score has been computed as a sum of individual scores for these streams, those 5 streams. Now there comes the question, why does it work? And there are 2 views. The first one, optimistic, is the view of what I thought when inventing this technique. And this is just a thought. If we were using open loop phone only unigrams, we have some distribution, but this distribution is actual sum of some other distributions which may be more discriminative for the speaker, because what I want to model is how people differs in pronunciation of specific phones, and moreover we have all the context from ASR. We look ahead from ASR, and it's kind of strong information, and this could maybe do something. And there's another pessimistic view, and this says that it's nothing more than somehow complexly quantized acoustics, because we can view open loop recognizer as somehow quantized acoustic system, and in the experiment we will see that these 2 approaches, maybe these 2 views, maybe hold together. Something's true on every view. So these were the results. These are on report 1, all place, 8 training conversations, ASR. So the first thing to show is that conditioning really helps. And for this I ran an experiment doing only unigrams on German, Spanish, Japan, and Mandarin, and then fusing them by summing the scores. So equal error rate is 13% when doing on the all data, excluding silence X, those crosstalk frames, and 7% when ASR triggers the time or the frames in which word occurs. So there is actually some information from ASR, but we believe that this, well, it's still not sure whether this triggering could be so good if done by some speech detector. Maybe there's some high level information from ASR which figures out that there's a word even if speech detector says that there's silence, but maybe something between 7 and 13 could be a result with some speech activity detection. And this should be compared to 2.7% of German, Spanish, Japan, Mandarin given ASR. Then another question arises, which is related to pessimistic view. What happens when we replace ASR by English or by another open loop phone? Is it really so strong? Is the ASR, does it contain so strong information, or can we use something easier? Maybe it's again for implementation purposes a good view that when we use ASR triggered, it's 4.3, and when untriggered on all the data, it's 7.6. And my best results were done on a little bit better system than this one, which is comparable to those experiments. This new system used additional conditioning on phone length. There's a mistake. There's the phoneme length because it's conditioned on the ASR phoneme length. This was just an idea that people may have different modes of pronouncing. So when pronouncing slowly and using long phonemes, there are maybe a little bit different distributions. And another idea is that maybe it's modeling some states of HMM, which is behind the phonemes. So English only given ASR gives 2.8. German, Spanish, Japan, and Mandarin gives 2.3, so we can compare it with that number, and everything together gives 2.1. Interesting is what happens if we replace ASR by manual transcript, and it's 1.6. But 1.7. Doesn't matter. So what I would like to extend this approach. I would like to examine other predictor schemes. So use something different than ASR, something what is not so computationally intensive, and use some external predictors, something like predictor of mood of the person, or predict. Maybe it can be done by the rate of speech. I will talk about it later. Then I would like to examine the robustness of approach. I would like to use something different instead of phones that will be more invariant to signal distortion, because in low quality telephone speech or something like this, people may confuse some, say, and maybe some other features than phones would serve to distinguish people as well and be more invariant to this. And of course, I will use this extended data tasks, so the results will be comparable, and I will continue development on switchport 1 and evaluate on switchport 2. So, other predictors. Baseline is triggered open loop phones. It was 4.3, so it's not that bad compared to 2.7, which is comparable to this. So maybe something like bigram phone recognizer, which is something like open loop, but having bigram capabilities of the language associated language model. It's still cheap, but it's more constrained than open loop. So I hope it could work better than this. And then I could add other external predictors which are in some way cheap or cheaper than ASR, but maybe add some other discriminability power. So I would like to condition that this is the example how could those predictors look. So additional conditioning by the rate of speech, and this is because we can estimate that people are using different pronunciation when excited or when not excited, and rate of speech can be something which we could measure and maybe measure some kind of excitement and hope that these probabilities will be different for those two. And one what's not written here would be using, instead of using phones when having phone recognizer, maybe using states of the HMN would be much better, because it's something like phone lines. And the last thing in other predictors is soft conditioning. When having speech excitement detector, it's kind of hard to say this is excited speech and this is not. You can have some fuzzy approach, some number, some probability of fast and slow, and in this equation, instead of probability given something, we could use this formula. So these two probabilities are taken from the model. This probability is computed from the input utterance by the detector of excitement. And it works in the way that when the detector is not sure, it answers with probabilities which are prior probabilities of this seen in the training, and it changes itself to changes itself as if there was no condition on slow fast. And when the predictor is quite sure, it's something like normal conditioning. So robustness, this concerns the other side, the other predictors. For predictor side, this is the predicted side. And the goal is to find some features which are not so sensitive to signal distortion. At first, I would like to see how actually phones are sensitive to this distortion, and I would like to try by adding noise to the signal, convolving signal with some impulse response of echo or Landstorff filter, and do some non-linearity to distort the signal, and finally use some combination of those, simulating some acoustic hard environment. As a baseline, I would use open loop phones, which I already have, and as first experiment, I would make equivalence classes from phones which are likely to be confused. So this probably make performance on clean condition worse, but on noisy conditions it won't be confused by interchanging of confusable phones, and may stay in this area, or maybe be even better than the original approach. I would like to try to use articulatory features instead of phones. I've been trying already near, but maybe not very hard, because articulatory features were in fact 2 times worse performance when predicting articulatory feature given the phoneme. And maybe the next experiment would be to use quantized vectors of several features instead of single one. So when I have open loop phones, I would do some quantization of vectors of these 5 phones to get a new feature. meet and use with it. But I think this is not this is just an experiment. This is not the goal. The goal is to find a single feature which will be extracted from the audio. So one of the experiments will be using vector quantization of acoustic features itself. So that's it.
So good morning, my name is Andrea Adami, and I'm going to talk about my work with modeling pitch and energy dynamics, which is under the prosodic group. So the goal of my work was to characterize and model speaker-dependent pitch and energy contour dynamics. So the motivation behind that one is, thanks to Jack Godfrey, is that there are speaker-dependent pitch energy deficits. What I mean by pitch energy deficits, how the pitch or energy contours relate when the speaker is speaking. One example is like pitch rising and energy falling at the word endings. And this can be characteristics of that particular speaker. A second motivation is that pitch and energy dynamics can convey speaking style. You know, when a person is nervous, it's like the pitch is really shaky, like mine, for example. And you have animated person versus monotone speaking style. Like usually, I'm not really animated. And the approach that we use for this is we start with the information that we got from SRI database, which is piecewise linear pitch slopes and energy contour. Then we convert this sequence, these slopes, into a token sequence, and then using the n-gram bag approach to model and classify that sequence. So how we do this? So from the SRI database, we have the raw pitch represented by the blue line and the stylized pitch represented by the red line in this first block. And the energy contour, we have only the energy. We don't have any slope information. So what we do first is to find the regions or the segments where the slope is the same. Then we can apply the same segmenting on the energy side to define, okay, I want to know what's with respect with this slope pitch, what's happening in the energy. So what I do, it's a linear regression, which is not well represented with this shape, but just by doing this and quantizing the slopes using the sign of the slope. I'm not doing nothing very complex. It's just the sign of the slope, if it's falling or rising. Then I merge these tokens, and then I have a sequence that characterizes what's going on between pitch and energy contours. And just with the sequence of 5 tokens, all combinations of plus and minus, and the unvoiced regions, I can get 19.6% equal error rate on the 8 conversations using bigram. And as a comparison, just using the pitch energy raw distributions with GMM, we can get 16.3%. But we have to realize this is just 5 tokens. Okay. But as you can see, this is the simplest information that we got, but we can add more complexity to this. And one of for how long it can keep this rising pitch and falling energy. So we integrate the pitch and energy slope duration to the tokens. So we quantize all the duration, giving the pitch, the slope, into 3-level quantization, which is short, medium, and long. So for each feature in this case, I'm just showing this plot because it's the same for both. Then we just add for how long the speaker is speaking this, in this gesture, he's using this gesture. And as you can see, with the result, just by adding the duration, is 13.4% equal rate, which means that it's a 33% relative improvement over just by using the slope tokens, which is pretty interesting. But this is not the only complexity or the only information that we can add, right? So another thing is all this pitch rising, falling is happening in some context, right? And so why don't we combine some context, in this case phone context, to the falling and rising of the pitch and energy. So we add the phone information. So we have a set of 43 phones. So we start with the predefined tokens that describe the pitch and energy contours. Then we overlap with the phonemes segments. So with the crossings of these two regions, we define what's going on for each phone. So, for example, in the off phone, we have that the pitch is rising, the energy is falling, and the duration is medium. But in this case, the duration now is quantized based on the phone. So before it was just everybody was in the distribution and we just quantized based on that. But now we are quantized depending on the phone context. And some cases where the phone can span over different pitch slope contours. We have two different, we can split this phone into like two or more pitch slope information. And with this approach, we can get 4.8% equivalent rate. So it means that, okay, context is helping. But we can say, oh, but this is because we are adding the phone. But if you look here, just the phone diagram performance by itself is 10.8. It's not giving me like that much of improvement. So, and I tried and I merged just the scores from the phone and the slope and duration. I could have got this 4.8%. So all these improvements not just because of the phone concept, but also the group of all these information, duration, pitch, energy, so. Okay, so just to summarize all the results, very impressive, right, with the color. Bear with me. Yeah, this is, so we start with the slope. Let me use that one there. Okay, so we start with the slope, just the slope quantization, plus and minus. We get 19.6%. Then we have the pitch and energy raw distributions, right? Using GMM. Okay, that's I'm just showing the GMM. The rest is of course the diagrams. Then I get 16.3%. When I add duration to the slope, I go from 19.6 to 13.4, which is the 33% improvement. That just the phone by itself, 10.8%. Okay. But when I fuse the result of my pitch and energy raw distribution with the slope duration, I can get a 9.1%, which means they have complementary information. It's not, I'm not replicating anything. Because we have to keep in mind that when I'm using these tokens, I'm not describing the value of the magnitude of the slope, but I'm just trying to characterize what's going on with the pitch and energy contours. They continue here. When I was coming down, I start with slope, then I add duration, right? You can also do a different track. You can add just phone. Now look at the duration. And comparing this to this, we see that phone is helping a lot. but the directions also helps to improve our results. And the final result, which was the fusion of the slope side, the best result with the slope information with my GMF, which gets 4%. So the conclusion is that adding more information or specializing the information that we deal with pitch and energy contours always give us improvement. And that we have different information contained in just the rod distributions and the slope contours. Slope contours. So the conclusion is the goal, this was a match. The goal was to extract now, pitch slopes energy can characterize. Of course, this is the simplest way, but we have to deal some points. As you saw in the beginning, the energy contour, the slope estimation, depends on the pitch information. This should be, in fact, separately, because I can show that the linear regression is not that good based on those regions. The linear fit does not provide accurate representation. Can you use something different? We saw that we saw some lumps in the energy contours. Can you use something like splines or quadratic regression? And we won't only use the slope. We can use something different because we are working with dynamics, and dynamics are not explained only by slope. And finally, is the n-gram. We just used n-gram. It was like the proposed work, and this is just local. And since this behavior or gestures happen across time, we want to model longer span time. So my work proposal is to analyze level of features and models that capture speaker-dependent contour dynamics. Okay. And this work is going to be done through three main tracks. The first one is to get a better contour modeling. As you can see here, this does not represent really what's going on this energy, right? But this was just a first approximation. We cannot depend on different streams to find information on energy, for example. We can use, so the whole idea is to do separate tracks or extract separately for each stream. And add new dynamics like acceleration. So not only slope, or we can model this like using splines. So one thing is to find how to model this. And work with the slope magnitude. I haven't worked with just the value of the slope. I was just quantizing to plus and minus. I tried to quantize more than plus and minus, but I was not successful with that. And we can bring some physiological constraints. How can you better model the energy? How fast can change? How fast the pitch can change? And this can drive my models to better estimate these numbers. Or is energy and pitch all the information that I have? Can I use something different? We have formulas. Or, okay, so you can say, formulas is pretty hard to get, precisely. Let's go for frequency band energy. What's going on in the frequency band energy? Because the energy is just squash all this. We are just summing up all the behavior happening each day. So we can go for this. Or different streams. And finally is, in the classifier part, in the modeling part, is that I use n-grams. Can use something that can map longer relationships between slopes, not just local, but something that goes farther than that. I've been working on discrete HMM since last week, and for just for the sake of presentation, I use the pitch energy slope and the duration, and I use it 17 states discrete HMM. The bigram performance is 13.4%. whereas the discrete HMM is 9.6%. As you can see, we can get much more of longer time relation between the slopes, which this is trying to picture based on which features I run this experiment. So, to wrap up, the whole idea is, let's get these features, let's model these features using these three tracks, which is better contour modeling, look at the different streams, we don't have only pitch and energy, and study better classifiers that well represent what's going on with this pitch or this extremes information. Let's not tie only to pitch. And just to make the work like broad and valid, I'm going to do all this work based on the NIS-Extend data test and sort of like using switchboard 1 as training, testing, and switchboard 2 as testing ground for this work. Thank you.
So I think, since I wanted to make sure all the grad students had the time to do it, if there was questions for the grad students, we can loop back through some of the slides if some of this percolated. I guess otherwise we have, so I just want to know if there are any questions from that. Otherwise we can loop into, if there's questions people have, and discussions about the SuperSID, I mean, any of the tasks that we did, or other questions or things that came up, not just for me, but for the team too. Jack?
Did you consider using phone classes instead of individual phones as the conditioners for the prosodic gestures?
No. That was I was getting this information from the SRI, so we tried to couple everything to the SRI database. So right now,
there's two ways in which class information, just off the top of my head. Vowel consonant differences, for example, could very well, vowels and different classes of consonants could separate out portions of prosodic gestures in a natural way. And also, since vowel classes tend to have intrinsic differences in energy, you could help to normalize the energy profile by separating out into vowel classes. That's just, I mean, I don't know whether it'll work or not, but you can try it. Where the vowels with higher first formants are going to tend to be more energetic intrinsically, and by conditioning on that, you would take out some of the, you would take out what is a false cue in energy, or in other words, just normalize the energy.
Andreas?
I had a question about this last of the work proposals. The difference between the diagram and the discrete HMM. From the picture of the HMM, it looks like it's, it just has one state per label, and unless you have higher order transition probabilities, I don't see how it could be any different from the diagram.
Yeah, we've been trying different. That was just the last.
Right, but so how come that the discrete HMM is any different? Does it have high order transition probabilities, or what is? I mean, the diagram is just a special case of an HMM with only first order markup assumption in it, and if you have one state per observation, then they should be equivalent.
Actually, it wasn't one state. The picture was a bit incorrect in that sense. There was a PDF associated. We didn't boot it up that way. It did a random init, and then when it came out, it had a PDF for all tokens at each state.
Okay.
So, he showed it there pictorially. The only ones that ended up actually taking their own state was we had start and end tags, like start and then a turn and then an end. Those got their own state because they just occurred uniquely. The other ones, they were not. We didn't see deltas in the distributions. It was kind of a setup. Questions for the other? Okay. Any other general questions or discussion, or does anybody on the team want to add, subtract, multiply anything? Aaron?
From your earlier presentation, we saw the really impressive 0.2 error rate, and I wondered if there were any particular speakers which really could not be discriminated at that level, and if so, what they look like.
They got this tall. I don't know. We didn't have the audio data here. And we didn't go into that analysis yet. I mean, it is a handful enough that we can look. Also, I believe, based on some previous listening, there's mismarks in there. There's going to be some errors you're not going to get right because it's mislabeled. But I don't know that it's, we haven't looked at that. We need to go back and listen to the audio. Mark?
Any ideas on how to characterize, you have 500 speakers, subsets of speakers, and how they work on different techniques? What is the probability of me picking a subset of 5 speakers from your set and all the techniques really work in game clusters?
You're right. We have not done that pooling out of by speaker itself. So the 520 were aggregated together in a pooled result, as we showed here, and it sort of gets to the error analysis of, are we finding, if you will, the goats, the sheeps, and are they perhaps relative to the technique that you're using? So you know that maybe these techniques work well on these speakers and these work well on these speakers. That's an interesting division of results that we haven't gone into yet, so I don't know the answer. Rich?
You might have said this, but I think I missed it. When you compute n-grams of the phonemes over time, for a lot of the things that you did, you actually had a phoneme label every frame, every 10 milliseconds or so, as opposed to at some non-uniform interval. Were the phoneme n-grams computed on the 10 millisecond labels, on the frame labels, or on the...
No. So the work, when we presented the things that Joe and Walt had been, where we talked about the n-grams, the parallel set using the PPRLM in the main talk, those were done on the token sequence itself.
So there's a different number of tokens for each language open loop.
That's right. So I guess, and when David did, when he had it there per frame and had the unigram result, it's sort of a weighted, there's a weighting of duration. So there is a distinct difference in there. Also, I'll point out that some people might have noticed that like in Andres and in Shen, there was some discrepancies perhaps if you said, well, you told me 4.8% equal error rate with the phones in the main talk, and I saw a 10 here and an 8 there. There are differences. It is consistent within each of their talks of what they focused on. For example, in Andre's talk, the 10%, when he said he did just the n-grams alone, it was actually the prawn n-grams from the ASR output. So it's not the same as the open loop. So there is some discrepancy between that and using the English open loop. I just want to make that clear when people saw some of the differences in there. But all their experiment results they had were self-contained and self-consistent for what they were presenting.
George has a...
Well, there's a question in the back. Yeah. My head points this way. We'll look at my finger.
I was just curious, have you tried the best 3 or 4 systems, including the acoustic GMM? How far you get? Or do you really need all 9 of them to be able to point to?
Well, Joe might have something to say about that. He just finished Fusion.
Yeah, so in fact, the best two-way combination ended up being 0.3%. Equal error rate. The best three-way fusion ended up being 0.27%. So as you can see, there's some diminishing returns happening quickly. And also, Doug's kind of modest. The GMM acoustic system dominates the high rank in these lists. In fact, you can find the top scoring system that doesn't have a GMM. And from that point onward, there are no GMM systems, and from that point upward, every fusion contains the GMM acoustic system, as you'd expect. And I can provide these results later on. These came out last night, just minutes before midnight. So, as Doug was saying, fusion's always the last thing.
We'll try to put it in the electronic version that gets posted. We'll just put a slide in there.
You usually work overnight anyway.
Well, yeah.
George, did you have a question?
So what was the top two?
What were they?
Top two, which were the GMM and the...
Okay, so the top two is the GMM UBM Kepstrom and the n-gram pitch slope conditioned on phones that Andre presented. The top 3 was, actually there's a tie that includes those same systems with the addition of the GMM UBM pitch with length conditioning, and that was also tied with the Ngram word idiolect system of George's, which is interesting, especially since the focus of our group wasn't to continue refinement on the idiolect word system. So that was still quite powerful in Fusion.
George? Do you?
Well, yeah, I mean, this is great. This is a very interesting, I mean, speaker recognition is a good thing to be working on. I'm sure everyone will agree with that. But, when you say there's this issue about on the phone system, ASR triggered, does that mean just that you ate out phones that are outside the duration, outside the word intervals, or what? What does the ASR triggered mean?
ASR triggered means that I only took those frames on open loop side for which there was phoneme and ASR output. So something like speech activity detector.
Yeah, okay, all right. And, you know, on this ASR conditioned system, it seems it's hard to resist the pull of GMM. Why not use GMM rather than just the phone labels for your probability calculation?
You mean the top one?
Rather than have the probability of open loop phone give a condition on the ASR, have a GMM condition on it.
Yeah, they are actually running this experiment.
Oh,
but
okay, you're ahead of me, fine.
It's still in the training phase. Or
I mean, we try to get GMM in this somehow.
It's in its contract.
Oh, and then I had one other question. The segmentation on the prosodic linear, piecewise linear system, the segmentation is, how do you determine segment boundaries?
The slope. So if the slope is the same in that frame, I have a segment.
Well, how do you determine the segments?
That's a question for
That's
SRI.
for Andrew. Yeah. That we are getting from the SRI database.
I guess what I would suggest is the possibility of using ASR output to determine the segment boundaries. That would help synchronize the features with word or syllabic information.
Yeah, but it doesn't necessarily make sense because you have pitch movements that go, I mean, that's why it's called super segmental. It goes across.
Well, we're having good luck conditioning things on words, so it doesn't have to make sense.
But to your question, the segments were determined completely without any recognizer information. We just ran the pitch tracker, which, by the way, is from Anthropic, or what used to be Anthropic.
Right, but as everyone knows, the more computation you spend producing the results, the better the results are. So,
we all do the same thing by segment here?
well, I mean, there are these piecewise linear fits that are built on segments. Segments determined by...
Not phonetic segments.
No, not phonetic. Well, I'm suggesting...
Stretches of speech which are prosodically, which are some approximation.
All I'm suggesting
is
is to just try to pull this somehow into the segmental phonetic information, either at a word level, syllable level, I don't know.
Well, so let me also add though, I mean, Andre was talking in his presentation about adding the phone conditioning on the segments, and he also did run experiments where he used word instead of phone. So that would be a slightly closer approximation, where he refined the chopping by the phone and added phone input.
Any last question?
The Fusion results are all for the 8 station training condition, is that right?
Yes.
Do you have any idea of how much gain you get from the high-level features when you only have 1 or 2 training conversations per speaker?
No, but we'll run that over lunch. We have the data. We just didn't run. We have the data in the experiment sitting there. We just didn't produce the result. That's an excellent question, though, to see the trade-off, and especially the re-ranking you'd like to do. Which drops off the plate, which comes up.
So you'll have three-dimensional dead curve.
So Fred has actually some closing comment here, but I just wanted to thank the team for all their hard work, and it was an excellent summer there. So
Thank Doug, our fearless leader, that we could not have done this without. Thank you, Doug.
I have just two short announcements. There are more handouts concerning this group and the group that's coming in the afternoon, but it's really for our visitors, so we don't have that many. So whoever are the visitors and are not resident here in the summer, feel free to take the handouts which are outside. And secondly, you're on your own relative to lunch. But we prepared a map for with lists of restaurants on the other side. Actually, there are almost no restaurants on Johns Hopkins campus because everything is being completely rebuilt and it's going to be much more splendid. At some future date, but right now there is nothing, all right? But there is something called number 5. So you will see here that there are these yellow spots, and the yellow spots are correlated with numbers on the other side. And we don't expect any gourmet food, but it won't poison you either. Well, are you asking me whether I can allow it or whether I will guarantee anything? I don't know. I don't have a key. I don't think so.
There is no plan to close the room, so please take your things with you.
Okay. Have a nice lunch. We're back.